All right, welcome to the last page. You made it. Congratulations. And let's go ahead and look at example 5. And we're going to use differentials to estimate the amount of metal in a closed cylindrical can that is 10 centimeters high and 4 centimeters in diameter if the metal in the top and bottom is 0.1 centimeters thick and the metal in the sides is 0.05 centimeters thick. And so I know you might know a different formula for this. We're getting you to get just used to the idea of differentials. I'm going to show how they can be applied to just certain, physical applications. All right. And so if there's another way you can do this, I'm glad. But I just want you to use differentials so that you have an understanding of how to use the differential. And so first thing we need some type of function or formula to represent the situation. And here to help with this is going to be volume, because I want to find how much total amount of metal is in our cylinder. And so the volume of a cylinder is going to be pi r squared h, where V is our dependent variable, R and H are going to be independent variables. So I want to find my change in Z, or change in V, which is going to be the approximation of dV, right? Which again, they're not the same, all right? Delta V and dV are different, but delta V is the differential, and then my differential is going to just be a good estimation of how much total metal is left in our cylindrical can. And so I'm going to go ahead and take dV, and again, dV is just the partial of, one of our independent variables. So I'll take the partial of R. So if we do the partial of R, that's going to be 2 pi RH, 2 pi RH, and times our dr, because that is our first independent variable. Plus, now let's take the derivative, our partial derivative with respect to h. So that's going to be just pi r squared, and then dh. And what dh and dr represent the total change in our x's, or in our radius, and dh represents our change in our y. All right, and we're going to use this to estimate the amount of metal. So dr we're going to use as our distance for the outside metal. And so that's going to, on the sides, and that's going to be 0.05 centimeters thick. And we're going to use the metal from the top and the bottom as dH. And so dH is going to just equal 0.2. 0.2 because the top and bottom is 0.1 centimeter thick, so you got to combine the top and bottom. I'm sure, hopefully you understand where the 0.2 is coming from. And so now our formula is just going to be dV is equal to 2 pi r, 4 centimeters in diameter. So if we have there's a hair on the iPad that I'm trying to get rid of. So if 4 is our diameter, then 2 is our radius. And then the height is going to be 10 centimeters high. And then our dr, our total change, is going to be 0.05 plus pi times 2, which is times 2 squared, or pi times, so I don't know where that. So from pi times 2 times our radius squared times dh, which is 0.2. Plug that into the calculator, and we're going to get 2.8 pi, which is approximately 8.8 centimeters cubed. All right, functions of 3 or more variables, it's the same, all right? And if we have 3 or more independent variables, then we're going to treat, doing the differentials the same, where, your delta x and your dx, your delta y, your dy, and in this case, your delta z, dz is going to be the same. In this case, w would be our dependent variable. So this is just sharing that, it's really not going to change if you have 3